Hey, welcome to Discrete Math. In this first video, we're going to focus on propositional logic, and we're only going to look at a few topics in propositional logic. Now, one thing you might wonder is what's the point of starting with propositional logic? In fact, why are we even starting with logic at all? And so I wanted to talk a little bit about that before we get into any of the math. So one of the main goals of the course is to help you understand how to write valid proofs and how to tell when a proof is valid and when a proof is invalid, because there's a lot of proofs that are written that are invalid. Even in high-level math journals, people sometimes write invalid proofs, and sometimes it can be difficult to tell when a proof is invalid. But during this first unit, when we look at logic, we're going to figure out how to tell when a proof is valid or when it's invalid. And the way we're going to do that is we're going to see what is a valid proof. We're going to see how are valid proofs formed. And when you write a valid proof, you can use axioms and you can use rules of logic, which can sometimes be called rules of deduction. So we're going to learn those rules, and we're going to start with logic in this course. And that will allow us to write proofs about other topics outside of logic. And in addition to logic helping us tell what is a valid proof and what is an invalid proof, it's also going to give us some useful notation for writing math. And we're going to talk about some of that notation in this video, and we'll see plenty of other notation in the next few videos after this one. So we're going to start with propositional logic. Propositional logic is a type of logic that deals with propositions. So it makes sense for us to talk about what is a proposition before we get into any of the details of propositional logic. However, before we even define what is a proposition, it will be useful to us to define another word before that. And then we'll use that word in the definition of proposition. And so the word we're going to define before proposition is a declarative sentence. So we're going to look at what is the definition of this. We're going to see some examples of declarative sentences. We'll see some examples of things that are not declarative sentences. And then we'll see what is the definition of a proposition. So a declarative sentence, this is just a sentence that states a fact. So let's look at some examples of things and see whether or not they are declarative sentences. So that first one, I'm not saying yet whether or not it is a declarative sentence, but we can look at it and we can see, is that a sentence that states a fact? Well, it's a question. The question's saying, who am I? So it's not stating anything, it's asking something. So this is not a declarative sentence. Let's look at another example. Okay, so we have a math sentence right here. X plus 1 equals 2. And it's stating a fact there. The fact might be true, it might be false, but it is some fact. So it's a sentence that's stating a fact. So it seems to satisfy the definition at the top for declarative sentence. And yes, that is a declarative sentence. Okay, we have another statement here. Do your homework. So is this a sentence that states a fact? So it's not stating a fact here. It's telling someone to do something, do your homework, but it's not saying that the homework is done or the homework is not done. It's just like a command. So that's not a declarative sentence. Okay, let's see a few more examples. Okay, so an exclamation, or I guess you could also see this one kind of like a command, good luck, like may you have good luck. So this one, it's not stating a fact. It's not saying that the luck was good or the luck was not good. It's just saying good luck, exclamation or command, however you want to see it. It is not a declarative sentence. Okay, here's another sentence. The Lakers beat the Celtics yesterday. So it's a sentence and it's stating a fact, a true fact. At least today it's true. And so this is yes, it is a declarative sentence. So this last one is another math sentence. 2 plus 2 equals 5. So this one, we know it's obviously false, but it is a sentence and it's stating a fact. It's just a false fact. So facts can be true or false. They don't have to be true. You can say the sky is blue, the sky is red. These are facts, but we're not saying anything about the truth value of those facts. So 2 plus 2 equals 5. This is a sentence and it's stating a fact. So it is a declarative sentence. Okay, and now one last one before we move on to the next slide. This is the most interesting one. That's why I saved it for last. This sentence is false. So it's a sentence. We know it's a sentence because it's calling itself a sentence, and it ends in a period and starts with a capital letter. And it's stating some fact. It's stating that it is false, that this sentence, the sentence that is talking about itself, is false. We're not saying whether that fact is true or false. We're just saying that the sentence is stating a fact. So this one is a declarative sentence. Okay, so that was several examples of statements that are either declarative sentences or not. And let's now go on to the definition of proposition. So a proposition is a special type of declarative sentence. It's a declarative sentence that is either true or false, and it cannot be both true and false. So it has to be true or false, but not both of them. So let's look at a bunch of examples, like the last slide, just to clearly see which ones are propositions and which ones are not propositions. So that first one, we saw that was a declarative sentence, but we need to see whether it's true or false, and not both. So that sentence has a variable in it, the x. If we set x equal to 1, then we would have 1 plus 1 equals 2, and this would be true. However, if we set x to 0, we would have 0 plus 1 equals 2, and this would be false. So this declarative sentence does not have a single truth value of true or false. It can have a truth value of true if we have x equal to 1, or it can have a truth value of false if x equals anything else. So this is not a proposition. Let's look at another example. The Lakers beat the Celtics yesterday. We saw on the last slide, this is a declarative sentence. And it's true that it's either true or false and not both of them, because it's true. The Lakers did beat the Celtics yesterday. So this is a proposition. What about this one? We have this math sentence from the last slide. We said that it was a declarative sentence. 2 plus 2 equals 5. And is it a proposition? Is it either true or false and not both? And the answer is that it is a proposition. It's false. It's definitely not true. So this satisfies the definition of a proposition. Let's consider this sentence from the last slide, the last sentence from the last slide. This sentence is false. So let's think about this sentence. Does it have a truth value? A single truth value of true or false, and not both of them. So this one is good to think about for a second. So I'll let you think for a few seconds about it. Feel free to pause if you want more time to think about it. So let's consider that sentence right there. So there's our sentence. And if that sentence was true, then this sentence is false would be true. So if the sentence is true, that implies that this sentence is false is true. So then the sentence is false. On the other hand, if we assume that the sentence is false, because that's the only other possibility, it's true or it's false. So if it's true, then we got that it's false. But if we assume that that sentence is false, then we're saying that this sentence is false is false. So if this sentence is false, then the sentence must be true. So if the sentence is false, then the sentence is actually true. So this sentence cannot have a single value of true or false and not both, because if it was true, then it would have to be false. And if it was false, then it would have to be true. So although that last sentence is a declarative sentence, it's not either true or false. So this one is not a proposition. This sentence is a paradox. And let's consider one last declarative sentence. So we have the sentence 1 plus 2 equals 3. And this sentence does have a value of true or false, and only one of them. And it is true because 1 plus 2 equals 3. So this is a proposition. Let's consider one last sentence. And this one is more interesting than most of the others, besides the paradox. So this sentence is a compound sentence. 2 plus 2 equals 5, and this sentence is false. So this sentence, we can ask, is it a proposition? Does it have just a single truth value of true or false, and not both of them? So I want to underline something important here. We have this and here. So if you have a sentence with an and in it, for that sentence to be true, both of the parts on either side of the and would have to be true. So for this sentence to be true, both of these would have to be true. The 2 plus 2 equals 5 and this sentence is false would have to be true for the whole sentence to be true. This one right here, that one's clearly false. 2 plus 2 equals 5. We know that's false. So the whole sentence, the 2 plus 2 equals 5 and the sentence is false. Taken together, the whole sentence is false. Because when you have an and, both of the parts have to be true to make the and true. So if the sentence was true, that would not work out because you cannot have a true conjunction, a true and here, where one of the parts is false. Now we can look at the sentence being false, and the sentence being false, that actually works out. We don't get any contradiction from that. So this whole sentence here, it is false. It's false because this component right here, this simpler proposition, 2 plus 2 equals 5, that one is false. And when you have an and with a false and any other proposition, it doesn't matter what the other proposition is over here. All that matters is this one is false. And as soon as one of them is false, it makes the whole thing false. So this declarative sentence, it is a declarative sentence, 2 plus 2 equals 5, and the sentence is false. It only has the single truth value of false. It's not true. It's false because 2 plus 2 equals 5 is false. And even though this part is true, this sentence is false. Overall, the sentence is false. So that component of the and is true. The sentence is false. The whole sentence taken together is false, even though the component is true. So this sentence, this declarative sentence, it is a proposition. And so that is the answer, yes. And now that we've defined declarative sentences and propositions, we can discuss exactly what the truth value of a proposition is. So given some proposition, we say that its truth value is true, and we denote that with a T if the proposition is true. And if the proposition is false, then we say that its truth value is false, and we denote that with an F. And we can look at a few examples of propositions, and we will label them with their truth values. So first proposition, the Lakers beat the Celtics yesterday. This one is true. So its truth value, we'll label that with a T. Here's another one, 2 plus 2 equals 5. This one's clearly false. So its truth value is false. We denote it with an F. 1 plus 2 equals 3. The truth value is true, denoted T. 2 plus 2 equals 5, and this sentence is false. So we saw on the last slide that this is a proposition, and we saw that it's not true because 2 plus 2 equals 5 is false, and this sentence has an and in the middle. So if one of the parts to either side of the and is false, then the whole thing is false. So the truth value of that proposition is false. Now that we've discussed declarative sentences, propositions, and the truth values of propositions, we're ready to discuss how to make more complex propositions from simpler propositions. How to build propositions, in other words. In order to write propositions in a shorter way, instead of writing all the words out every time we refer to them, we're going to use variables to represent the propositions. These variables will be lowercase letters like P, Q, R, and S. Now, when we look at propositions, the most basic propositions that we can consider are called atomic propositions. So an atomic proposition is just a proposition for which no part of the proposition is a proposition besides the whole proposition. So in order to see some examples of atomic propositions and propositions that are not atomic, let's look at the next couple sentences here. So first, the Lakers beat the Celtics. So we can look at this proposition here, and we can look at all of the parts of it that are not the whole thing. So parts like the Lakers beat the, beat the Celtics, like these kind of things. And we can see that none of these are propositions. So none of the parts of this, besides the whole thing, the Lakers beat the Celtics, is a proposition. And I want to note here that the Lakers and the Celtics, we will think of these as indivisible. So we will not consider this that I just circled as a part of the whole proposition. Just like we wouldn't consider this as a part, splitting a word in the middle. So we're just going to treat the Lakers as a single word and the Celtics also as a single word there. Otherwise, you might say Lakers beat the Celtics is a proposition. But saying the Lakers is just a single word fixes that issue. So we will assume that. And the Celtics will also be treated as a single word. So this one is an atomic proposition. So there's no simpler propositions inside of this. Here's another proposition. The Lakers beat the Celtics and the Warriors beat the Pistons. So we can look at the parts of this proposition. And this one's longer, so it has many more parts than the first one. But it's easy to zero in on the parts that we want to consider. This part right here, the Lakers beat the Celtics, and the second part, the Warriors beat the Pistons. And we can see that both of these parts, this one and this one, they're both propositions. So the Lakers beat the Celtics, that was an atomic proposition. The Lakers beat the Celtics and the Warriors beat the Pistons. This one is not atomic because it has parts besides the whole proposition that are propositions themselves. So we have atomic propositions, and we can take those atomic propositions and connect them to form compound propositions. And on the next few slides, we're going to look at some different kinds of connectors that we can use. And in the next few videos, we'll look at more different kinds of connectors and what these connectors mean. And we're going to start with what is called the negation. So suppose that we have any proposition, and we'll write that proposition with a lowercase letter p. The negation of this proposition, the negation of p, is written as I've denoted on the slide here, and it's said as not p. So what does it mean? It means it is not the case that p. Sometimes not p, you might see it written as not p. That's another notation that's used in some places. Sometimes people might just write it with the word, not P. I've seen that too. There's a lot of different ways you can write the negation. If you're ever confused about some notations being used, it's fine to ask about it because there's multiple possibilities that you might see in different resources. So let's consider an example and what happens when we find its negation. So here's an example. We'll suppose that little p is the proposition that 1 plus 1 equals 2. And if we take the negation, not p, that's going to be the proposition not 1 plus 1 equals 2. In other words, it is not the case that 1 plus 1 equals 2. A simpler way we can say this, we can say not p as 1 plus 1 does not equal 2. And in the example that we just considered, note that the original proposition p, 1 plus 1 equals 2, that was true. So p had truth value t. Not p, on the other hand, had truth value f. It was false. So now let's consider another type of connector, which is called the conjunction. And a simpler word that you've seen probably before to describe it is and. So given two propositions, P and Q, the conjunction is just P and Q. So we'll denote the conjunction of P and Q the way that I've written it on the slide, which you can say in words as P wedge Q. So that specific notation, that one right there, the upwards arrow is a wedge. But when we say it in propositional logic, we just say it as P and Q. And there's a bunch of other ways that people use to write and besides this wedge. So this wedge is what I use. Most of the books I've read use this, but people also use P and Q. I've seen that pretty often. People also just write the and out like I did on that bullet, P and Q. And there's other things too. So if you're ever confused about it, just ask, because it's possible you'll see several variants. And I want to note that when you have two propositions, P and Q, and you take their conjunction, and you want to see whether it's true or false, the only way for the conjunction to be true is if both P and Q are true. So for the sentence P and Q to be true, you need P to be true and you need Q to be true. You can't have either one of them be false, or else it messes up the whole conjunction. So let's look at some examples. Suppose that P is the proposition 1 plus 1 equals 2. And Q, we'll suppose, is the proposition the Lakers beat the Celtics yesterday. So we can write P and Q, this new compound proposition, and it's just the proposition 1 plus 1 equals 2 and the Lakers beat the Celtics yesterday. Now in this example that we just considered, we can look at what were the truth values of P, of Q, and of their conjunction. So in the example, P had truth value of T. Q had truth value of T as well, because 1 plus 1 is equal to 2, and the Lakers beat the Celtics yesterday. That means both parts of the conjunction are true, so the conjunction P and Q, it also has truth value of true. Let's look at another example. Suppose that R is another proposition. It's a proposition 1 plus 1 equals 3. So we can look at what's the truth value of R. 1 plus 1 is not equal to 3. So the truth value of R must be false, which we write as an F. And that means that Q and R has truth value of false, denoted F. Why is this? Well, Q is true, so that's not what's making the conjunction false. What's making the conjunction false is the R. So as long as one of the parts in the conjunction is false, that makes the whole conjunction false. The only way for it to be true is if they are both true. So Q is true, R is false. That whole conjunction, Q and R, is false. So now we're going to consider another type of connector that looks like the conjunction, but upside down. So a disjunction. So again, suppose that we have two propositions, P and Q. The disjunction of P and Q, we write it like P V Q. So we have the P, we have the Q, but now instead of a wedge between them, we flip the wedge upside down to make a V. So we write a disjunction with a V instead of a wedge. And the disjunction, what it means is P or Q. So instead of P and Q, disjunction is P or Q. And just like the conjunction, there's multiple ways to write a disjunction. So another way I've seen of writing a disjunction is like this, P or Q. And of course, like this, the P or Q right there. So either of those ways you'll see. And there's multiple other ways as well. So for a disjunction, the rule is different than a conjunction. Recall that for the conjunction, the only way for the conjunction to be true was for both of the parts to be true. With a disjunction, you don't necessarily need both of them to be true. You just need at least one of them to be true. On the other hand, if they are both true, that's okay too. So let's consider some examples. Suppose that P is the proposition 1 plus 1 equals 2, and Q is the proposition the Lakers beat the Celtics yesterday. Now we'll consider the disjunction of P and Q, which is written P, V, Q here. And if you see it in other places, you might see other notation. So just ask about it if there's any confusion. And this disjunction of P and Q is just the proposition 1 plus 1 equals 2, or the Lakers beat the Celtics yesterday. Recall, as we observed on the last slide, the proposition P has truth value of true, denoted T, because 1 plus 1 is equal to 2. The proposition Q has truth value of true, denoted T, because the Lakers beat the Celtics yesterday. And that means that the disjunction, P or Q, this also has truth value of true, denoted T. And that's because at least one of the parts of the disjunction is true. In fact, both parts of the disjunction were true, which is fine. You can have both parts true, you can have only one part true. As long as at least one part is true, the disjunction is true. So the only way for a disjunction to be false is if both parts are false. So we'll consider another example now. Suppose that R is the proposition 1 plus 1 equals 3. And recall that we observed on the last slide that R has truth value of false, which is denoted F, and that's because 1 plus 1 is not equal to 3. We can consider the disjunction of Q and R, though. The disjunction of Q and R, it's going to have truth value of true, denoted T. And the reason for that is because Q, the proposition the Lakers beat the Celtics yesterday, that proposition is true. So even though R is false, even though 1 plus 1 is not equal to 3, since we have Q true, since we have the Lakers beat the Celtics yesterday is true, that means that the disjunction of Q or R, it must be true. So as long as at least one of the parts is true, the disjunction is true. And since Q is one of the parts and Q is true, that means the disjunction is true. So we're almost to the end of this video, but we have one last topic to consider, and this topic is a very useful method for reasoning about propositions. And this method is the use of truth tables. So truth tables are just tables where we have a row for each possible truth value of the atomic propositions. And we build the propositions that we are trying to consider in the truth table. So we build it from the atoms. And these truth tables are a useful and simple way to determine when compound propositions are true and when they are false. And when I use the word when here, I mean for which truth values of the atomic propositions are the compound propositions going to be true or false. So when we're talking about which truth values of the atomic propositions. So that word when is a shorthand for the possible truth values of the atomic propositions. So let's see what that means here. Let's look at some simple examples. So we'll consider the connectors that we defined on the last few slides, not, and, or, and we're going to make truth tables for each of these. And we're going to see for which possible truth values of the atomic propositions do we get the conjunction, the disjunction, and the negation to be true or false. In other words, when are these compound propositions true or false? So first table, let's look at the negation. This is going to be the smallest table. This table only has 2 rows because when we take the negation, we only have a single atomic proposition. We'll call that proposition P. We can use any letter we want there. The negation, not P here. Propositions, atomic propositions, they have 2 possibilities for their truth value. They're either true or false. If P is true, then not P is false. On the other hand, if P is false, then not P is true. So that's our truth table for negation. And this tells us when the negation is true and when it's false. So when P is true, the negation is false. And when P is false, the negation is true. Okay, let's look at another truth table now. We will consider conjunction. Now this truth table will have more rows, and that's because there are more atomic propositions in a conjunction than in a negation. we have a column for P, we have a column for Q, and we have a column for P and Q. Now we need to consider all of the possibilities for the atomic propositions. P and Q are our atomic propositions here. So P can be true and Q can be true, and P can be false and Q can be false. And we can also have either combination of one of them being true and one of them being false. So we can write T, F, and F, T. And these are all the possibilities that we can have for the truth values of P and Q. Either we can have P true and Q true, we can have P true and Q false, we can have P false and Q true, or we can have P false and Q false. Now that we have all of these possibilities listed out, we can just evaluate the truth value of the conjunction on each line of this table. If P is true and Q is true, then the conjunction of P and Q, that's true. If P is true and Q is false, then the conjunction of P and Q is going to be false. Because for a conjunction to be true, both of the parts have to be true. And I'll mention here the parts on either side of the conjunction. There's a word that's used to describe these. It's not too important to know this word, but it's a word you might hear sometimes, so I might as well mention it. These are called conjuncts. So the parts on either side of the conjunction, they are referred to as conjuncts in some places. So I might sometimes use that word, and if I do, that's what it means. So if we have P false here and Q true, we can evaluate the truth value of the conjunction P and Q. That's going to be false again, because for a conjunction to be true, we must have both conjuncts true. Finally, we can look at the last line. When P is false and Q is false, clearly the conjunction there is going to be false. P and Q is false because neither of the conjuncts is true. So the truth table for conjunction, we can notice an interesting fact here that only one line of the truth table has a true in the conjunction column, and the other three lines are all false. Let's do one more truth table. And if these truth tables are a new idea for you, that's okay. We're going to get lots of practice with the truth tables in the next few videos and in class. But we're going to do one more before this video ends. So hopefully this one will help give some more idea of how to do these truth tables. So the last truth table we'll consider today in this video is disjunction. Now this truth table will have the same number of rows as the truth table for the conjunction, and the same number of columns. We'll have columns for P and Q, and then we'll have a column for P or Q. And we consider all the possibilities for the atomic propositions P and Q. So we'll list them out again. They can either both be true. We can have P true and Q false. We can have P false and Q true. Or we can have them both be false. And now we can evaluate the truth value of the disjunction. And I'll mention another word here. Not too important to remember this word, but you might see it in some place in the future. And it's good to know what words are when you see them. So disjuncts, probably pretty predictable from the word up here. So the parts on either side of the disjunction are known as disjuncts. So if we have P true and Q true, then the disjunction of P and Q is also going to be true. Because for a disjunction to be true, we just need at least one of the disjuncts to be true. And in this case, both of the disjuncts are true, so the disjunction is true. If P is true and Q is false, then the disjunction of P or Q is going to be true. Because recall, for a disjunction to be true, you only need at least one of the disjuncts to be true. And in this case, P is true, and that's enough to make the disjunction true. Let's consider the third line. When P is false and Q is true, the disjunction P or Q, that's still going to be true. And that's because Q is true. As long as at least one of the disjuncts is true, that makes the whole disjunction true. And since Q is one of the disjuncts and Q is true, that makes the whole disjunction true. Finally, the last line. When we have P false and Q false, the disjunction P or Q, that's going to be false. And it's because neither of the disjuncts are true in this case. So it's not true that at least one of the disjuncts is true, which means the disjunction is false. So for the disjunction to be true, you only need at least one of the disjuncts to be true. But if you don't have either of the disjuncts true, then the disjunction is false. And so notice what's interesting here is that only a single line evaluated to false for the disjunction. You only get a false when both of those disjuncts are false. On the other hand, the other three lines, they were all true. So it's like we took this table up here and we replaced the F's with T's, and then we flipped everything. So there's three F's, they turned into three T's at the top when we flipped it, three T's here, and that T right there, it turned into an F at the bottom when we flipped it. So it's kind of interesting. And we'll see more about the relationship between conjunction and disjunction in the next few videos and in class. Thanks for watching.